Any questions? Where should we begin? Can you do 3.3, 1, and 2? Okay, so I'm gonna circle these in blue. So 3.3. So let's look at 3.3, 1, and 3.3, 2, right? Okay. So let me include it in the blank sheet right here. So I'm gonna copy this. Take a screenshot and then paste it here. We have another piece of it here, right? Oops. All right, so here we have an approximation of a binomial random variable, and we're going to be using the normal distribution to approximate. Okay, so a binomial distribution, if you recall, is discrete. It's a discrete random variable, and what we're using is a continuous random variable to approximate the discrete binomial random variable. And so it says we have a 65% of the population is in favor of a proposed rise in school taxes. Approximate the probability that a random sample of 100 people will contain part A, B, and C. So let's look at part A. So before we begin, we should let certain things be true. So let X be number of people in favor of proposition. And it's out of 100 people, right? That's the sample. And it's binomial at the moment. And so with the binomial, if we look at the binomial, we have certain parameters, don't we? So what are our parameters? We got N, we got P, and associated with P, we have Q, which is 1 minus P. Now, what does N represent? It represents the number of trials. So how many trials are there? There's 100. Each person is a trial, quote unquote. Okay, does everybody follow? And then P, what is P? P is the probability of a success. And how do we define success in this context? We define it as those who are in favor. So those who are in favor is considered to be a success. So if you're in favor, it's a success. Now, what's the percentage? In this case, the probability, it's 0.65. And then the automatic failure, probability for a failure is 0.35. Everyone follow so far? Any questions? We're all good? And so then after this, what do we need to figure out? We need to figure out the expected value, which is N times P. That's what a binomial random variable is known for having its expected value. So it's simply 100 times 0.65. It's a very easy calculation because it's only 65. And then what's the variance? The variance is what? N P times 1 minus P. So it's 100 times 0.65 times 0.35. And when you compute that, you get 100 times 0.65 times 0.35, and you get 22.75. Okay? Now, why is this important? Because now part A asks us, find a probability that at least 50, so X is at least, is greater than or equal to 50, okay? But at the moment, we're looking at this as if it were a binomial. So if I wanted to compute this straight as a binomial random variable, I would have to find a probability that X equals 50, X equals 51, X equals 52, all the way to X equals 100. You could also use your calculator and use the complementary probability, which would be 1 minus the probability of X being 49, 48, 47, all the way to 0. Okay, you can also do it that way. But the idea is that, you know what, we're going to approximate this. We're going to approximate using what? The random variable, the normal random variable. So we're going to treat this as a normal random variable. That is the approximation. We're going to make believe that this is a normal. Now that changes things. Now recall that the binomial distribution has a shape. Hold on 1 second. Sorry, guys. Hold on. I'll be right to recording. Okay, so where were we? So I was saying that if you recall, the binomial distribution, any kind of binomial distribution, has a very symmetric shape, reminiscent of the normal random variable. So the bigger the n becomes, right? The more the probability distribution has a curve, like a bell-shaped curve, such as a normal distribution. So it makes sense that as n gets bigger, we utilize the normal distribution to approximate the binomial distribution. And so, for example, if I wanna just make believe this is 50, right? And so what I'm saying is I want to find the sum of the probabilities from 50 all the way to 100. So to account for that, what's called the continuity correction, I want to include 50, 51, 52, 53, but now instead of using the binomial, I'm using the normal. For this normal, I want to include a little bit to the left of 50, particularly 49.5. And I'm going to include 49.5 and go all the way to the right. So that's why this will be, accounting for the continuity correction, this will be 49.5. Again, all we're doing is going from binomial random variable distribution to a normal one. And I accounted for the continuity correction by subtracting by 0.5. Okay, we either add by 0.5 or subtract by 0.5. So to include the 50, we subtract by 0.5. If I didn't want to include the 50, if this was strictly a greater than without the equal to symbol, then I would add by 0.5. So it would be 50.5 instead. That's just a really minor detail. So now that we're in this world of normal distribution, what we care about is the mean. So this becomes mu, and this becomes sigma squared. And we care about sigma, which is the standard deviation, right? So those are the parameters that are important to understand for normal distribution. You need to know what the mean is, mu, and you need to know the standard deviation, which is sigma. Those are the two parameters. So there's two ways to go about this. We either use our calculator or the table of Z, the table of the Z scores that we have, that we originally started with. So the way to do the one with the table is we standardize or normalize the normal random variable x. By doing that, we have to subtract by mu and divide by standard deviation. And we do that also to 49. So 49.5 minus mu over standard deviation. So this here becomes z. This becomes the standard normal. Why does it become the standard normal? Because in subtracting by the mean, subtracting the normal random variable by the mean and dividing it by the standard deviation, what we just created what is a normal distribution where the mean is 0 and standard deviation is 1. So that's the reason why we do that. So we have z is greater than, and then we can plug in these values. You can plug in 49.5 minus mu, which is what, 65, and then divide that by the square root of 22.75. Okay. And so then we have 49.5 minus 65. And this is negative 15.5 divided by, and then we can divide that by the square root of 22.75. And then I get, when I subtract and divide by this, I get negative 3.2496. So that's quite interesting. And then to compute this, you can use the table. Let me see if I remember where I placed that table. I think it was 17. No, 16. Yeah, this is it. Okay. So let me place that here. So this is z. So this is like saying I'm in the standard normal. And I don't even need this anymore. And this is 0, this is 1, this is 2, this is 3. This is negative 1, this is negative 2, this is negative 3. This is like saying find the area underneath the curve at negative 3.2 and find this area here. That's what we're finding. We're finding the area. But the problem is the table only gives us the area to the left of the curve, and the x values, as you can see, or the z values, they're all bigger than 0. But I have a z value that's smaller than 0, it's negative. And we can just round it to the nearest 2 decimal places there, or 0.35325. Not a big deal. Because of the symmetry, if you notice, this area here will be the same if this was on the other side. 3.25 here. This would be the same area to the right. So the area to the left, so I can rewrite this by saying the area to the left of negative 3.2496 is the same as the probability as z. Well, no, pardon me. This is saying that this is z that's bigger. So this should be on the other, sorry, pardon me. This would be this area here. All of this. This is not indicating the correct area. So the area is all of this. Is everything to the right of 3.2496. And so what I meant to say is that this is going to be equal to 1 minus the probability of z to the left of negative 3.2496. But to find the area to the left of this is the same thing as finding the area to the right. So this would be the same thing as saying 1 minus the probability that z is to the right of positive 3.2496. So there's going to be a lot of this stuff here. So then to find the area to the right of 3.2496 is the same thing as finding the area to the left, 1 minus the area to the left. So I know it's going to be a little bit of confusion, might be, but it's the probability to the left of 3.2496. And so what comes down to is that when you distribute this -1 here, that negative sign, the ones will cancel and that negative p becomes positive. So really, this is the probability that z is less than 3.2496. Okay, so all of this stuff here is just an intermediate step. The important thing is because of the symmetry, the area to the right of this point here is equivalent to find the area to the left of this positive z value. Okay, so then we can look at the table, and 3.2496, so 3.24. So it's going to be somewhere 3.2, somewhere here, 0.994. So that's roughly what the probability will be. Any questions about this part A? Does everyone follow this, or any questions at all? So we need to show the intermediate step. So all of this stuff is more for you guys to see where I went. If you guys can go from here to here, that's fine. And this whole procedure here is if you use the z-score table, which I will do my best to provide for all of you for the test, for the exam, okay? But you could have also done this with your calculator. So if you have your calculator, you don't need all of this. So this is using the table, okay? This is using table. Now, what if I just want to use my calculator? If you want to use your calculator, you can go from here, from this step here, x is greater than or equal to 50. Then you do continuity correction, and then you say x is greater than 49.5, okay? Now, when you use your calculator, you're not simply just going to use it and just plug in the numbers and then get the answer and then move on. I want you to, when you present it on your paper, on your workspace, I want you to tell me what you did. But of course, you don't have to tell me every single button that you press. But I do want you to tell me your lower. So when you use the binom, right, you're going to use, you're going to use the normal CDF, right? This is going to be the normal CDF function. So I want you to do give me the lower, give me the upper, give me the mean, give me the standard deviation. Because that's what they asked you when you plug in. So the lower here would be what? 49.5. The upper would be what? It would be E99. The mean, what was the mean again? The mean was 65. And the standard deviation was the square root of 22.75, which is what? The square root of 22.75 is 4.769. Okay, and then it's gonna spit you out a number. So let me show you using my calculator here. So second distribution, I'm gonna go to normal CDF. And then I'm gonna place the number 49.5 as the lower bound. Then the upper bound would be second E would be 99. Then the mean would be 65. Standard deviation, standard deviation would be 44.769. And then when you press this, you get 0.994. So that's going to be the probability. Okay? Does everybody see how we got that using the z-score table or the calculator? Either way, we get the same thing. Where did you get 22.75? Well, we started our problem. We started our problem over here. So this stuff here is extremely important. If you don't know how to get here, then this problem becomes very difficult. So we first treated X as the number of people in favor of the proposition, and this was a binomial because the number of people who are in favor is a binomial random variable. You either are in favor or not in favor, right? So N is the 100 because we have 100 people and either they're in favor for it or are opposed to it. P is the probability that the person is in favor. There's a 65% chance that you are going to be in favor. Q is the probability of failure, so 35% is assumed to not be in favor. And so we calculated the expected value of a binomial random variable, which is N times P. And we calculated the variance of the random variable, which is N times P times 1 minus P. So I'm just multiplying 100 by 0.65 and 0.35. And when I do so, I get the number 22.75. That is the variance of this random variable. But I'm not going to use the variance. I'm going to use the standard deviation. So that's why we use this number here. The standard deviation is the square root of 22.75, which is approximately, so I should maybe be a bit more explicit here. Standard deviation is the square root of 22.75, which equals 4.769 approximately. And so what we're doing is we're utilizing the standard deviation from the binomial random variable into our approximation of the normal, using the normal distribution to approximate the binomial distribution. Okay, so that's pretty important. But then once you have this, part B and C is very much, it's very similar in style. So part B asks between 60 and 70 inclusively. So this is probability that X is equal, less than or equal to, greater than or equal to 60 and 70. But of course, I'm going to use continuity correction. I want to include 60 in it, so I subtract by 0.5 and I get 59.5. And I want to include 70, so I add by 0.5 and I get 70.5. Okay? And then from here, I can either use my calculator, but just make sure you understand how to use your calculator. You use normal CDF, the upper 70.5, the lower 59.5, the mean is 65, and the standard deviation here is 4.769. You plug that in to your calculator and you should get the next answer. Normal CDF. The lower bound is 59.5. The upper bound is 70.5. The mean is 65, and then the standard deviation is that. And we get 0.75, 0.7512. Does this make sense? Does everybody follow how to do that using your calculator?
So, Professor, To clarify, part A, the only reason why it has an upper bound is because the upper bound for part A is because there is an infinite amount, but for part B, it only starts at 70.5.
That is right.
Okay.
Yeah. Yeah, you can see that from what x is, right? X is strictly bigger than 49.5, so it means it could be as big as you want x to be. So there is no upper bound. So we say it's infinity, which your calculator doesn't know how to compute infinity. It just computes a really large number. So we write e to the 99th power, which is just saying, this is the same thing as saying 10 to the 99th power, which is humongous, right? But then here, x is bounded by 70. So 70 is going to be, well, and if we treat this as a normal random variable, 70 is our upper bound, but then we're converting this or approximating it using a normal distribution. So we're adding a 0.5 for the quote unquote continuity correction. So we use the 0.5 to include that number 70, because in the world of continuity, continuous random variables, right, it's very difficult to select just a single value. And to account for that single value 70, we just accumulate a little bit to the right of it. That's why we add by 0.5. It's a very arbitrary number, 0.5. It could be 0.4, 0.3, but just for simplicity's sake, we tend to just add by point or subtract by 0.5.
So Professor, while using the calculator, the similarity that you use for like x greater than 60, you choose 59.5. May I know if it's only x is less than 50, so what probability number should I use for the upper bound?
If x is less than 50,
Yeah.
so if you have something x is less than 50, right?
Yeah, that's right.
Yeah. So if that's the case, remember x is a normal. We're treating this as a normal random variable. And if you remember, continuous random variables in general, not just normal, but all continuous random variables, they tend to go from negative infinity to infinity. Those are the values of x. So it's implied that this here is negative infinity. The same way we imply that this is bigger than, or infinity is bigger than x. There is no upper bound. Well, there is, but we're treating it as if a really big number. So for something like this, the lower bound, you would use negative 1e99 or something like that. Something to that effect. Does that make sense? So it's going to be negative.
So for the upper bound, there is not, what should I like use for the calculator to find out?
Well, the upper bound here, you say 50, right? The upper bound would be 50. Yeah, x is less than 50.
Didn't we need to use like the 0.5, something like that for this?
Yeah, so if this was a binomial distribution, so then if you're telling me you want to do this, okay, so then you would do the continuity correction, and then you would say, yes, I include the 50, right? Well, actually, okay, so this is just a very slight problem, okay? So I'm gonna show you two different scenarios. So this could be it, right? So both of these here, I'm treating this as if x is binomial, okay? It's binomial. So in the first example, x is strictly less than 50. If you're less than 50, I'm not including 50.
Yeah.
I'm including 40, 49, 48. So then the proper way to treat that with the approximation, right, where x is normal, I would write this as x is less than 49.5 because I'm not including 50. But, however, if this is less than or equal to 50, I am including 50. Because of that, I'm going to add by 0.5. So this would be less than 50.5. So the lower bound for either one, will still be negative e to the 99th power. It's just a convention that we use. But the upper bound will be different. The upper bound here the upper bound here will be 49.5, and the upper bound here would be 50.5.
Oh, so you always like increase by 0.5 if it's like equal, less than or equal to the other.
Yeah, less than or equal to, you add by 0.5. But you just have to read this carefully. Just read it carefully.
Okay, sure. Thank you.
Okay, so then, like, for example, part C, just to look at part C, look, it says fewer than 75 in favor, okay? So the way we write this, the way we would write this would be what? P is what? X is less than 75. Do you see this is exactly this kind of scenario where we have strictly less than. Because it's strictly less than, I'm not going to include 75, so I can subtract by 0.5 for the continuity correction. So I'm gonna get something like this instead. Okay, and then to compute this, the lower bound would be negative 1.899. The upper bound would be 74.5. And then the mean and standard deviation, right, which is going to be 65 and 4.769. You put that in your calculator and you should get the desired answer. Okay. So then I'm just gonna rewrite this as 74.5, and then this will be negative E99. Okay, so I can also change the arguments on the home screen itself, and then when I press enter, I get 0.976, and that should be the answer.
Professor,
Yes.
I'm actually getting the answer as a negative number
For which one?
for this one, for the one you just did.
You're getting a negative number for part B and C?
So just see.
For C, okay. How did you plug it in the calculator?
I plugged it into the calculator. Yeah.
Yeah. Okay. How did you plug into the calculator? Did you use the normal CDF?
Yeah.
Okay. Did you plug in negative? Did you do negative E?
Oh, I see what I did. I reversed it. That's what I did.
You revert. Oh, yeah.
Yeah.
So then when you reverse something, it's like saying the area, like, you know, when you calculate the area underneath the curve, you have a lower bound and an upper bound. When you switch it, you swap the lower bound and upper bound, then you get a negative area, the negative signed area. So that's why you get negative. Mhm.
Thank you.
Okay, any other questions about this part? This question, 3.31. Now, I know we don't have that much time, but number 2, I know originally you said number 2, right? Rakib. Number 2 is very much the same. So what I'm gonna do is I'm just gonna give you the setup. A lot of this, guys, is just the setup. Hopefully you start to see that most of these problems, like especially the ones in the same subcategories, right? When they're underneath the same subcategory, they're pretty much the same kind of question. And it's just setting up the question correctly is the hardest part of it. Once you're able to set it up correctly, you should be okay. 4.3 is just integration. Let me see. 4.3, yeah, most of 4.3 questions. Well, 4, number 3, yeah. All of these questions are a lot of it. Well, number 3, number 4, and number 5, they're mostly just integration. So if you know how to find the expected value of a using the density function, which requires integration, and finding the probability using a density function requires integration, and you finding the variance will also include some integration. So a lot of number 4, 3/5 of number 4 So number 3, number 4, number 5, underneath this heading is really just integration. So again, I'm just gonna set up this question here. I have 1,000 independent rolls of a fair die. So immediately, okay, it says compute the approximation to the probability that the number 6 will appear. So X represents the number of 6. Number of times that 6 appears when rolling a fair die. So what's the probability of rolling a fair die to be a 6? 1/6. What's the probability of not rolling a 6? 5/6. How many times are we rolling the die? 1,000 times. Again, I can't stress this enough. You have to be able to identify your random variable, which in this case would be binomial, and you have to identify the parameters of the binomial. If you don't have this, you have nothing. From here, you can say, oh, I know exactly what the expected value is. It's n times p, which is 100, 1,000 over 6, whatever that number is. And I know the variance of the binomial immediately, n times p times q, which is 1,000 over, so let me just write this slowly. So it's 1,000 times 1/6 times 5/6, which is 5,000 over 36, whatever that is. And then once I have this, I want to find what's the probability that the number 6 will appear between 150 and 200 times inclusively. I want to find a probability that X is between less than or equal to, because we're using inclusive, right? So it's 150 and 200. That's if I treat this as a binomial, but I'm not going to do that because I'm going to approximating using the normal. So the probability, because of the less than or equal to symbol, I'm including 150 and I'm also including 200. So I have to add and subtract by 0.5 accordingly. So this would be 149.5 and this would be 200.5. Do you guys see that? So this is the continuity correction step. And then from here, you can use your calculator, or again, you can use the Z table score. But to use the Z table, you have to convert all of this. You have to normalize all of it, right? You would have to do X minus mu over sigma. This would be 200.5 minus mu over sigma. This would be 149.5 minus mu over sigma, and all of this. I'm finding the probability of this. But since we have a calculator, you can just compute using the normal CDF. You just have to be mindful of what your lower bound is, which is 149.5, the upper bound, which is 200.5, the mean, which is 1,000 over 6, and standard deviation, which is the square root of 5,000 over 36. You put that all in your calculator, and you should get an answer. You should get the correct answer. Okay, so this question, if you notice, very much the same structure as the one we just did. So we identify the random variable, we computed, we gleaned off the parameters of my random variable by reading the problem correctly. We figured out this is extremely important because if you don't got these two things here, then you can't use a calculator or the Z-score table for computing the probability. So you need to do this. This is exceptionally important, essentially important. And then once you're able to do that, then you can find the probability. So any questions about these two problems? Is this clear? Is the way we're solving this, is it clear?
So, Professor, if it was says exclusively, isn't the like probability like the continued correction would be the same?
No, exclusively. If I say if they use the word exclusively,
Mm-hmm.
which is probably not going to be the case, they're assuming that 200 and 150 are not included.
Mm-hmm.
So this would be a strictly less than symbol. If this is strictly less than, then this number here will not be 149.5. It would be 150.5. And this number would not be 200.5. It would be 199.5. Just by saying that these two numbers are not included. So it's
Oh,
inside of 150 and 200. Okay?
okay,
So it would not be the same.
okay, gotcha.
Okay, any other questions about this? Is that good? Okay, especially 3.1 question 2. So let's do that one first, okay, Chaitanya? Let's do 3 point, you said 3.1? Yeah, 3.1 question 2. Oops. Okay, so these problems are all very much the same, again, same kind of problem. We want to find the Z naught in this case. Normally, we want to find the probability of a number being less than a number. Oh yeah, and there's a typo here. This should be equals, okay? Not less, not minus. This should be an equal. And I corrected it on the answer sheet. Um, so what we're doing is the opposite of what we've been doing so far. We've been finding the probability. In this case, we're finding now the z-score that gives us the given probability. So this is like, so for part A, right? We want to find the probability that z is less than some number, z naught, which we don't know, that equals 0.8172. So again, this z, the z random variable stands for the standard normal, right? Should be the standard normal random variable. And again, what is the standard normal random variable? It's the bell curve where the mean is 0 and the standard deviation is 1. So I'm going to have some kind of bell curve like this. And then this is 0, this is 1, this is 2, this is 3, -1, -2, -3. And I want to find some point, I don't know where it is. There's some point, call it Z naught, that the area to the left of that point to that point is 0.8172. This is the area to the left of Z naught. So if I were to use my table, right? If I were to use the table for this problem, I will go to my table and see where is it that I have 0.8, what is it? 0.8172. I just forgot the number. 0.8172, right? So 0.8172. So you scan it, 0.817. This is 1.5, this is 1.8. So it looks like 0.8172 is somewhere in between here, right? Because we don't have 0.817, we have 0.82, we have 8.8159. So it's somewhere in between here. You see that? So it's going to be somewhere between 0.90 and 0.91, somewhere in between. So that would be roughly what? Where is this? So Rizwan says 0.90. Yeah, I'll write it somewhere in between. So it looks like, yeah, this is way off here. So it looks like it's some number here, 0.905. That would be my z-score, right? Now, to get a better, more accurate number, I would use my calculator instead, because the calculator is much more finely tuned for this. So to use a calculator, you go to second vars and you use the inverse norm. Inverse norm. It's not what I want to do. Let me go back. So you go to inverse norm. So that's what this is important. So here, for this problem, you have to tell me I'm using the inverse norm function. And then you have parameters. You have the area, you have mu, you have sigma, and then you have the tail. So that's why it's important. That's why it's important to draw, to give you a visualization of what we're having here. So what we're having is that the area, again, this idea of probability and area are synonymous for this class. Area is probability, probability is area. So this 0.8172 probability is the area. That's what the area is, 0.8172. The mean and the standard deviation are the standard ones, 0 and 1, standard. Every standard normal, the standard normal random variable only has the mean being 0 and standard deviation being 1. And now the tail, where's the tail? The tail is basically saying in what direction is the area going? Is the area to the left of the z, or is it to the right? Because the way this is written, it's the area to the left. Why do I know it's to the left? Because of this inequality. Z is to the left of z naught. It's smaller than, right? It's less than. So it's to the left. So we use the word left. Okay? And so when we do that, right? When we do that in our calculator, I'm going to plug in 0.817201, and I'm going to highlight left, and I'm going to go down and paste. When I do that, look what I get. I get my Z nod is 0.90474 ... right? Of course, this gives you way more precision than the table, because the table only has a finite number of decimal places after the decimal point. But your calculator has a few more decimal places to go. And do you notice how close it is? Do you see how this was like an estimate? The one that we use for the table, this is from the table, from Z table. We estimated, we just averaged 0.90 and then 0.91, and we say, oh, it's between 0.905. But look at this. It's quite accurate. That estimate that we made is quite accurate. This is from calculator. Okay. Does that make sense? And the same thing goes for the rest, guys. You just have to interpret all of this. So what is this going to be? Again, what is this? This is the area. Now, what is Z going to be in between? Z is between two numbers, Z and Z naught. I don't know what they are, but I know that the area in between them, is 0.215. Again, I can use it. I can do this using the calculator, the table, or the calculator. So in the calculator, I'm going to do the same exact thing. Inverse norm. Area is 0.215. Mu is 0. Standard deviation is 1. The tail, however, in this case would be the center. So then when you look at that in your calculator, the center. The center is what? This is 0.21501. Then I'm going to put, oh, sorry, I don't know why it's froze on me. This is the center here. And then when you press the enter, you see how we get two numbers in bracket form? One of them is the negative version and the other one is the positive. just Z naught is equal to 0.2728. And that's going to be that Z-score that gives us the area in between it. So Tanya, does that make sense?
Professor,
Yes.
my calculator doesn't have the tail option either.
Yeah, so if it doesn't have the tail option, if yeah, that's okay. I believe the default is to the left. Correct? Correct me if I'm wrong. So if you were to try to do the same problem part A, if you did the same problem part A and you didn't have the left, right, did you still get this number?
Yeah.
Okay. Because you still got the same number, it means that your calculator by default is doing to the left. The TI-84 and I guess the other ones, they have more features, more options for you, right? So if that's the case, if you only use to the left, if you don't have the center, you can still do it. It's just a bit more work for you. Because what you're gonna have to do is so if you don't have that center function, then what you're gonna do is a bit more involved. What you're gonna do is gonna be this. So this is without center, right? This is without center, and this is if you don't have a calculator, you can also do the same idea. You can apply the same reasoning for the table, for using the table. So if the area underneath these the curve between these two numbers is 0.215, then what's the area outside of it? How would you calculate that? Does anyone know?
One minus.
Right. So you do 1 minus, right? You do 1 minus 0.215. And if you do 1 minus 0.215, what do you get? You get 0.785. So that number represents the area to the right of Z naught and to the left of Z naught combined. What if I want to find just the area to the right or just the area to the left? We'll then have to take this number divided by 2. So then when I do that number, 0.785, and I divide it by 2, what do I get? I get 0.3925. So this area here is 0.3925. This area is 0.3925. Do you guys follow me? So then for those people who don't only have the left function by default in their calculators, for those of you who have the TI-83, right? Or if you don't have a calculator and you just have the Z-score table, then what you're going to do is you're going to find the area to the left of Z naught, which would be the area in between here, which is 2.15, and the area 0.3295, 0.3925. So to find this number here, the probability that negative Z naught less than Z naught equals 2.15, sorry, 0.215, this is equivalent to finding the probability that Z is less than Z naught, but that equals what? 0.215 plus 0.3925. Does everybody follow what I just did here? 0.215 plus 0.3925. That's going to give me what? 0.6075, right? Does everybody see why they're the same? It's the same thing. Me finding this number is the same thing as finding this number for this different looking equation. This number here is different than this number because I'm including everything to the left of Z naught. This number is only between Z naught and negative Z naught. There's symmetry there. You guys follow that? So then now, if you use your calculator, you do the same exact thing. You do inverse norm. When you do inverse norm, you're gonna not put 0.215, you're gonna put 0.6075. Mean is 0, mean is standard deviation is 1, and I'm not gonna use the center function, I'm gonna use the left. By default, those of you who don't have this feature have the left option. And so when you paste this, you get 0.2728. Do you see how it's the same? It's the same as what we did above for those with the center function. It's the same, 0.2789, 0.27809. It might be off by a little bit, but it's not really significant. Does everybody follow this? Are we in agreement with what's going on? So does everybody see how you can get around the fact that you don't have a right option? You don't have a center option. This is only if you have a calculator that does that feature. But just because you don't have that calculator doesn't mean you can't do it. You just have to understand, what does the probability represent underneath the curve? That's the area. What does Z naught represent? That's like the bounds. Can you quickly go over how question D would work in the calculator? Yeah. So D is probably the hardest one in this set, in these problems here, in these 4 little problems, because see here, the C1, it's area to the right. So if you have the right feature, that's easy. Or if you don't have that right feature, if you don't have a calculator, if you just have a Z table, then this area to the right, you do 1 minus the area to the right, which will give you the area to the left, and then you can figure it out that way. Part D, however, you have a kind of an asymmetry. You have an asymmetry here. So let's treat this with a little bit more care. So part D, right? We have the probability of negative 2.14 is less than or equal to Z, less than or equal to Z naught, and this is equal to 0.6831. So either you have the left option, the right option, no option. Table is, this is still, think about this a bit more. So how do we approach this? Again, drawing this out will always be helpful, always. Standard normal. So we know everything about the standard normal. It's very symmetric. And negative 2.14 is somewhere here, right? Negative 2.14, somewhere there. And Z naught, I don't know where it is. I'm just gonna make believe it's somewhere here. Z naught, somewhere here. So the area underneath here is this, 0.831. So I'm finding the area in between 2 numbers. One of them I know, the other one I don't. So what would I do instead here? I would want to figure out, what is the area to the left of 0.214? What is this area? And you can do that in your calculator. You can find out what that is. So then let's do that. So I have to go back now to normal CDF, because that's what gives me the normal CDF. Hold on. I don't know why. Okay, the normal CDF gives me the area to the left, right? So I'm going from negative infinity to negative 2.14. Standard deviation is the mean of standard normal is 0, and the standard deviation of standard normal is 1. Paste. Boom. What do I get? I get 0.01617 dot 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 dot. Okay, so that's the area to the left. Does everybody understand? You have to work with what they give you. So this is the area to the left. This is the area right here. So equivalently, this can be restated as the probability that Z is to the left of Z naught, where the area is 0.6831 plus 0.016. You can put 1 or 2. It doesn't matter so much, but I'm just gonna cut it right there. If you want, you can make this a 2. Again, that's very insignificant in terms of what you decide to do there. And then when you add 0.6831 plus 0.0161, I get a 0.7292. So look what I just did. I reformulated this seemingly strange inequality, asymmetric inequality, to something that I know how to do. I know how to do this. I do inverse norm. And this is the area to the left, 0.7292. This is mean is 0, standard deviation is 1. You put that in your calculator, and you should get the answer. Inverse norm, the area is 0.7292. Mean is 0, standard deviation is 1. Area to the left. Paste. Boom. I get 0.61. So my Z naught is 0.6104 if I round it to the 4 decimal places. Does that make sense, James?
So Professor, I have a question now. Why is negative 2.14 as an upper bound?
Why is negative 2.14 an upper bound?
Yeah.
Okay, so let me just reiterate why I treated it as such for a moment. I treated it as well, actually I should rewrite this. Pardon me. This should not be greater than. It should be less than. It should be less than.
Oh.
Yeah, that was my mistake.
Oh.
So it's less than. Yeah, because I want to find the area to the left. So that was my mistake. I don't know why I put greater than, less than. So these symbols definitely matter a lot, right? When you do these kind of problems. So Z is to the left of 2.14. That area to the left is 0.01617. This is this area. So when you add this area, you got it. So when you add it with this is exactly what we get here. And then you do inverse norm and you get Z naught. On the answer sheet, it's the answer is not the same. Let me see. Is it not the same? Yeah, it could be a little off. I think that might be a typo. Let me check. This is what 3 point yeah. Yeah, so you can check this on your own, right? So if you say, okay, looks like something's wrong, so we can just finalize whether there's a mistake or not. So how would we do that? Well, we can use normal CDF, and then we plug in negative 2.14, And the upper bound would be, let's try what the answer choice says, 0.5223. So if I, so 0.5223, right? That's what the answer choice is, right? So if you paste, you get 0.6831. Oh, okay, and then we do normal CDF. And let me see what happens if I, so it looks like it is 0.5223. So let me see what happens if I plug in 0.61 instead, 0.6104. I get 0.713. So something went awry here. So let me just check if I wrote in the correct things. So let me just redo this here. This step here, I'm gonna put negative E to the 99. Oops, should put negative. And then the upper bound, I'm gonna put negative 2.14. So I do get that. Then I'm gonna add that to 0.6831. Okay, so I think I did the addition incorrectly. So that was my mistake, guys. So the addition is where I made a mistake. I think I put it incorrectly into the calculator. I did. So instead of putting 0.0161, I put 0.0461. So that's the mistake on me, okay? So the answer sheet is correct. So let me just make the correction on the actual work. So on the calculator, I just mistyped it. This number is a bit bigger. It shouldn't be this big. It should be instead, what was it? Let me correct that here. So it should be a 1. So it should be 0.6992. Okay. And so then because of that, this is going to change. And so let's do that one more time. So this is going to change, right? So then you do second, you do inverse norm. And then the area to the left would be 0.6992, and everything else is okay. And then when you press enter, you get 0.5221. 0.5221, which is very much the same as 0.5223. So there could be some, because of the rounding error, there's a lot of rounding here. The last probably the last digit might be off by a little, but I'm not gonna take away points if you're off by like 5 or 4 or 3 units from the last digit. And I'm gonna make the answers being rounded to the nearest 4 decimal points. That's why they rounded to the 4 decimal points, just to try to minimize round off error, which will inherently be part of this. But yeah, so that was my mistake with the 0.0611. So I think what could have happened is that I should have rounded up. Instead of putting 0.0161, I should have added 0.0162. So if I would have done that, that could have probably changed things. And you see, I also kept it as 0.6992 instead of rounding it to 0.6993. So all of those things, like they have a compounding effect. So if this was a 3 instead, what would I get? I'll get 0.5. You see how one little digit makes one extra little change. So again, there's round off error. None of these answers are precise. The only precise way is if you put all of these decimal points, 0.69927732252. If you put that, even that is not precise because it's truncated. But regardless, the mistake was found, and the answer sheet is technically still correct.
So would you accept both 0.5221 and 0.5223?
I would, as long as you provide the work, and I see that your approach is consistently made correctly. The 0.6992 and the 0.6993 is not significant. It's not a significant difference, right? If it was 0.6992 and 0.72, like then that's a different thing. That's a much more significant of a difference. But a 0.6992 and a 0.6993 is just a round off error, which is not significant enough to say, oh, you don't know what you're doing. I wouldn't do that. Does that make sense?
Yep.